And let's get into it with one of our favorite interstellar experts, Harvard professor Avi Loeb. Professor, welcome back. Starting with these new images from ESA's Mars Orbiter, what stands out to you? According to the European Space Agency, mission scientists weren't sure how well these images would turn out with a dim target so far away. Normally, these instruments are used to image objects more than 1,000 miles below. The color and stereo surface imaging system CASAs on EXIMs wasn't designed for this kind of imaging. For months, astronomers had been waiting for this encounter, hoping the world's fleet of Martian orbiters would glimpse the visitor as it crossed interplanetary space. When the day came, the object passed within about 30 million kilometers of the red planet. Close enough for cameras aboard ExoMars TGO, Mars Express, Tian-1, Hope, and NASA's Mars Reconnaissance Orbiter to try to capture it. Then, for a while, there was silence. Data releases stalled. NASA's operations slowed under a U.S. government shutdown, and the absence of images spawned the familiar online speculation that sometimes flares when science moves slower than imagination. Astrophysicist Avi Loeb, known for his outspoken commentaries on interstellar phenomena, stepped in to clarify the situation. The lack of immediate data, he explained, was no sign of conspiracy, but a symptom of ordinary bureaucracy. Long delays, he wrote, are not a signature of extraterrestrial alien intelligence, but rather of terrestrial human stupidity. Large research teams require time to process and verify data before release. And with many U.S. agencies partially shut down, the normal cadence of scientific communication had simply slowed to a crawl. In his view, patience, not paranoia, was the appropriate response. When the first confirmed images finally arrived, they came from the European Space Ice ExoMars Trace Gas Orbiter, TGO. Its color and stereo surface imaging system CASAs captured a small diffuse sphere of light extended modestly toward the sun. An echo of what the Hubble Space Telescope had seen months earlier when 3 Atlas was 10 times farther away. Then Hubble's camera had revealed a faint 4,000 kilometers wide glow slightly elongated in the direction of sunlight. Now near Mars, the same structure was visible. Smaller, sharper, but unmistakably familiar. The differences were technical, not physical. The TJO's mirror, only 13.5 centimeters across, gathers 300 times less light than Hubble's 2.4 mirror. Its angular resolution, about 2.3 arcsec pixel, translates to roughly 340 kilometers at the object's distance. Even the largest estimate for 3I Atlas's nucleus, around 46 kilometers, was far smaller than a single pixel. The spacecraft could not resolve the solid body at all, only the halo of dust and gas illuminated by the sun. Brightness data from NASA's Spree Observatory had already suggested a wide range of possible nucleus sizes. If the surface was bright and icy, the object might span tens of kilometers. If dark and carbon-rich, perhaps only a few. Even a 5 kilometers nucleus would contain some 33 billion tons of material, enough mass to keep its trajectory stable and prevent detectable deviations from outgassing forces. The absence of measurable non-gravitational acceleration implied that material was escaping slowly and symmetrically without giving the body a noticeable push. The CASAS images reinforce this interpretation. The brightest region around 3EI Atlas measured about twice the width of background stars, roughly 680 kilometers across. That was an order of magnitude smaller than the halo seen by Hubble. But the difference made sense. The smaller telescope aboard TGO could capture only the dense inner region of the glow, not the fainter outskirts visible to Hubble. When the brightness was corrected for the stronger sunlight near Mars, the two data sets lined up neatly, showing that the comet's outgassing had remained steady over the preceding 3 months. Other spacecraft joined in. The Mars Express orbiter used its Omega and SpyCam spectrometers. China's Tian-1 and the UAE's Hope mission also aimed their cameras at the faint interstellar visitor. But the most anticipated data were still to come from NASA's HiRISE instrument aboard the Mars Reconnaissance Orbiter. With its 50 centimeters mirror and exquisite optics, HiRISE could achieve a resolution of 30 kilometers per pixel, 10 times sharper than TGO. Those images, once processed, were expected to deliver the best constraints yet on the nucleus of an object that came from another star. A deeper mystery soon emerged. The object's trajectory through the solar system lay just 9 degrees off the ecliptic plane, the thin disk along which the planets orbit. For a random interstellar body, such alignment is extraordinarily rare. The first two interstellar visitors, Oumuamua and Borisov, had arrived at steep angles, 123 and 44 degrees, respectively. The odds of another traveler entering so close to the ecliptic were less than 1%. At first glance, one might expect debris from the Milky Way's disk to arrive along similar planes, but the solar system's ecliptic is tilted by about 60 degrees relative to the galactic midplane, 10 times greater than the inclination of 3I Atlas. Stars in the galactic disk move in gentle vertical oscillations known as epicyclic motion with random velocities about 10% of their orbital speed. Any material ejected from their planetary systems should arrive from all directions, not a privileged one. The trajectory of 3 Atlas so neatly matching the planetary plane therefore stood out as a genuine anomaly, an alignment that begged for explanation. Subsequent modeling traced the object's galactic path backward and found a possible origin near the boundary between the Milky Way's thin and thick disks, a turbulent region shaped by ancient gravitational mixing. There, old stars and young ones overlap, their differing orbital velocities stirring the interstellar medium like currents in a vast celestial ocean. 3I Atlas may have been cast out from this frontier billions of years ago, a frozen relic from an epoch when the galaxy was still settling into its present form, a messenger from another system carrying chemical and physical records of its birth. As 3 Atlas approached the inner solar system, new telescopic observations showed that it was growing more active. Its tail lengthened, its coma brightened, and the sublimation of volatile ices intensified as it neared the sun. Spectroscopic analysis revealed familiar gases, carbon dioxide, water, and organics, similar to those of solar system comets, though subtle differences hinted at chemistry born in a different stellar nursery. Despite its acceleration towards perihelion, the object remained structurally stable, showing none of the odd tumbling motion or non-gravitational drift that had made Oumuamua so perplexing. Further imaging confirmed a sharply defined tail stretching hundreds of thousands of kilometers into space, consistent with earlier predictions that sunlight and radiation pressure would sculpt its escaping gases into a classic cometary plume. The structure demonstrated that 3I Atlas was behaving like a familiar comet, but moving at interstellar speeds of over 30 kilometers per second relative to the Sun. By late 2025, astronomers had assembled a coherent picture, an active interstellar comet with a nucleus probably between 10 and 40 kilometers across, steady outgassing, and a remarkably flat orbit. The combined data from orbiters around Mars and telescopes on Earth provided the first interplanetary view of an extrasolar visitor, a milestone in collaborative space science. The implications reach far beyond a single comet. Interstellar objects like 3 Atlas are natural probes of the exchange of matter between planetary systems. Each carries isotopic fingerprints of the environment where it formed, its temperature, metallicity, and exposure to radiation. By comparing those signatures to solar system comets, scientists can test whether the processes that build planets are universal or vary across the galaxy. Matching chemistry would imply shared origins. Stark differences could point to alien conditions in distant star systems. Spectroscopic data from Mars Express and ExoMars are expected to sharpen that view. Instruments such as Omega, SPIAM, NOMAD, and ISIM were designed to detect faint emission lines from carbon dioxide, methane, and water vapor. Even partial detections could yield the first direct chemical comparison between an interstellar object and solar system material. Meanwhile, NASA's MAVEN spacecraft used its ultraviolet spectroscopy to look for volatiles invisible in optical light, adding another layer to the investigation. The study of 3 Atlas has become a case study in scientific restraint, a reminder that skepticism and curiosity must move hand in hand. The object's peculiar alignment and remarkably steady activity invite explanation, not speculation. It is in moments like these, When mystery and data coexist in uneasy balance, that science proves its true discipline. Rather than rushing to sensational conclusions, astronomers across the world have chosen patience, waiting for calibration files for confirmation from multiple instruments for the slow accumulation of evidence that transforms wonder into understanding. This discipline is not the absence of imagination, but its tempering. Each new image of 3I Atlas forced researchers to test competing hypotheses. Was its near-perfect ecliptic alignment a coincidence or a clue to some larger galactic pattern? Did its modest but consistent outgassing reveal an ordinary comet or a fragment forged in an environment unlike any in our solar system? Every question was allowed to mature through observation rather than impulse. The object's very ordinariness in some respects. Its gentle glow, its chemically familiar gases became as fascinating as its anomalies. In its quiet consistency, 3I Atlas taught a broader lesson that the universe often hides its most profound truths behind patterns that appear deceptively simple. Now, as 3I Atlas recedes into the darkness beyond Mars, it continues its escape from the sun's gravity at more than 30 kilometers per second, bound for the deep void between the stars. It will never return. Yet in its wake, it leaves a legacy of data, spectra, images, and trajectories that will be studied for decades. Each pixel and photon gathered during its brief passage through our neighborhood adds another layer to humanity's understanding of how material from distant systems drift through the galaxy. These fragments of light are in essence cosmic fingerprints, records of temperatures, compositions, and histories that no other probe could deliver. In them lies the story of the Milky Way's invisible commerce, the slow, steady trade of matter between worlds. The event marked a historic first. For the first time, orbiters around another planet played a direct role in observing an interstellar object. Mars, once merely a distant target of exploration, briefly became a scientific outpost for galactic research, a new node in humanity's expanding network of observation points across the solar system. The red planet's orbiters built to study Martian dust and atmosphere turned their lenses toward a visitor from another star, transforming local instruments into interstellar observers. It was a demonstration not only of technical versatility, but of vision. The understanding that every platform, wherever it may orbit, can contribute to a broader cosmic conversation. For theorists, the encounter poses lasting questions. Why this geometry? Why this stability? Why this rare alignment that defies probability? What forces billions of years and light years away set 3 Atlas on a path that would intersect our solar system so precisely? And what does that precision tell us about the dynamics of the Milky Way? The hidden circulation of debris that threads through its spiral arms like unseen rivers. Each of these questions leads to others about the rate of interstellar travel for comets, the efficiency of planetary ejection mechanisms, and the larger scale patterns of galactic evolution for observers. 3 Atlas has done something equally profound. It has redefined preparedness. The collaboration between Earth-based telescopes and orbiters around Mars has shown that when the next interstellar object arrives, and it will, humanity will be ready to study it in real time from multiple vantage points across the solar system. No longer will these visitors appear and vanish with only a handful of images to their name. They will be tracked, analyzed, and understood as part of a growing body of interstellar science. The forthcoming Vera C. Rubin Observatory, soon to begin its all-skies survey, promises to transform this field. With its 8.4-meter mirror and 3.2-gigapixel camera, it will sweep the southern sky every few nights, detecting faint moving points of light that earlier surveys would have missed. Its automated systems will instantly flag objects on hyperbolic trajectories, bodies not bound to the sun within hours of discovery. What once took months to recognize, as with the Oumuamua and Borisov, will soon be detected almost in real time. Each new traveler will bring its own story. Rocky shards of shattered worlds, icy relics from the birth of distant suns, or remnants expelled during stellar cataclysms. Their compositions will reveal whether other planetary systems share our chemical blueprint or diverge into alien forms. Together, they will build a galactic census of planetary debris, showing how common Earth-like chemistry may be across the Milky Way. 3 Atlas has already shown what can be achieved when instruments across multiple worlds work in concert, and when science resists the temptation of sensationalism in favor of patient collaborative inquiry. In the end, the significance of interstellar objects lies not in their mystery, but in their message. They remind us that our solar system is not an isolated island, but part of a dynamic cosmic ecosystem. Dust, rock, and ice drift endlessly between stars, carrying with them the stories of countless worlds. 3Y Atlas, faint and fleeting though it was, offered a glimpse of that vast exchange. A frozen emissary from the depths of the galaxy, caught for a moment in the light of our sun before vanishing once more into the dark.